So we discussed what is the RMS value, the root mean square value of any function. If a function x of t is given, then you have to square it, find out the mean, meaning you have to integrate over one time period divided by the time period, and you have to find the root. This is the RMS value, right? Let us now discuss the RMS values of some prominent functions. Okay, so we already saw for a sine curve, when the maximum value is given by Vm, here it is minus Vm, then RMS value is going to be Vm by root 2. What if it is a half sine wave, meaning that only the positive half cycle is present? So this will be the entire time period. Okay, so in this case the RMS value is going to be Vm by 2. This is called as the half wave rectified sine wave. That means it will have only the positive peaks. Now what is a full wave rectified sine wave? All of the cycles will be present and all of the cycles will be positive. Now the time period is now reduced by half compared to this one. What is the RMS here? This will be same as this sine wave. Okay, the reason is x of t we are squaring. So whether it is positive or negative will not matter anymore when you are finding the RMS value. Okay, so if the magnitude is same, then you're going to get the same value. What will this be? Vm by root 2. You can see a similar case in the case of the step input and the square wave. Let us say this is the step input. This value is Vm. In this case, the RMS value will simply be Vm. Now you take the square wave. That means for half of the time it will be plus Vm, half or whatever time it is. And the other half of time it is going to be minus Vm. Okay. Then what will be the RMS value? This also will be Vm, because this magnitude is Vm only. Forget about the sign. Just positive Vm, negative Vm. So this will be having the same RMS value as this. Okay. So this one is a good point to remember. It can come in handy. Now you can take a pulse waveform. So that means there are pulses like this. In this case the RMS value is going to be Vm by root 2. You can find out. You can use the mathematical expression for the RMS expression and you can see, verify whether these are the correct values. And next we have a sawtooth waveform. So this is in the shape of the sawtooth, right? So that's why it's called a sawtooth waveform. This maximum value, it is Vm. So in this case it is going to be Vm by root 3. The same goes for a triangular wave. This is Vm, then here the value you're going to get Vm by root 3. So these are some RMS values of some prominent waveforms. If you can remember, well and good. It will be always advantageous. Now another expression that comes in handy is if a function is having multiple functions. So that means let us say this is x1 of t plus x2 of t plus so on. So this can be a sine wave or it can be a square wave, step input, triangular input, whatever is the case. What will be the RMS? How can you express the RMS value of x of t in terms of the RMS values of each of this? So that means RMS value of x1t is known. Let us take this to be RMS 1 and this RMS is also known, RMS 2. Then you can find out the RMS of the equivalent wave. So what will that be? Effective RMS is going to be the root over the individual squares of the RMS value. Okay. So this first RMS value you take it, you square it, plus the second RMS values you square it, plus so on. The entire root is going to give you the effective RMS. For example, let us take a voltage function which is having a V0 value, constant value, plus Vm1 sine omega 1t plus Vm2 sine omega 2t. Then what will be the effective RMS? The effective RMS, that means the RMS of V of t. This is going to be root over, what is the RMS value of V0 for a constant function? The RMS is same, V0. You square it, plus, here what will be the RMS value? The maximum value divided by root 2. So Vm1 divided by root 2 whole square plus Vm2 divided by root 2 whole square. This will be the effective RMS. Okay.